I thank the organizers again for this invitation and being part of this nice conference. I kind of feel like I don't deserve to wear this fancy schmancy device. I don't have an MBA degree, and I'm not selling you anything, so but okay. So this is recent work that I've been doing with my student Dipankar Roy, who's over there. Dipankar, please raise your hand. Okay, he's there. If anybody wants to simulate exclusion processes, he's the go-to guy for you. And this work is on the archive. Let me start with the simple model, and then I'll explain the more general model with multiple species. So you consider a one-dimensional lattice with L sides. You have two kinds of particles. You can think of them as charges. You have pluses and minuses. And also you have some vacancies, which I call, there are n0 of them, and they are fixed for the dynamics. So in the bulk, the rule is the following. So whenever a plus is followed by a vacancy, it wants to go right with rate 1, and the flip happens the other way around with rate q. And similarly, minus wants to go to the left and against a vacancy, and a plus minus also wants to interchange. Yeah. So all of these happen with rate 1 in the forward direction and rate q with the backward direction. So you can think of an electric field pointing to the right, and q you think of as less than 1. So it's mostly pluses are going to the right, minuses are going to the left, but occasionally they will sort of go the other way around. On the left boundary, so here something funny happens. Only the minuses can be replaced and can be replaced by pluses with rates alpha and gamma respectively. And similarly on the right boundary, the pluses and minuses can interchange each other. Okay? So you think of the pluses as coming from the left, moving to the right, and exiting from the right. And you think of the minuses as coming from the right, moving across the system and exiting. Mostly. You think of gamma as being less than alpha and delta. So in this case, the steady state distribution can be calculated exactly through what is called a matrix Ansatz. The steady state probabilities can be written as a product of matrices which depend on the state that you're looking at. If the state is tau 1 to tau L, you have x sub tau 1 up to x sub tau L, and you sandwich it by a Brownian vector, and you get a number. And that's essentially the steady state probability up to some norm. And so these matrices satisfy this algebra, and this problem was solved exactly by this Japanese gentleman. And I think he must have had a very hard time submitting it. I mean, referees must have given him a very hard time because it's published in this not so good journal, but it's really a very hard and very intense, solid piece of work. Okay, so he manages to compute the phase diagram, and you can see it's highly non-trivial. So you define these two parameters A and B in this way, this horribly complicated form, using all the parameters. And you define this xi naught to be 1 plus rho naught by 1 minus rho naught, where rho naught, so you're taking the limit of the system size going to infinity such that the number of zeros is fixed. I mean, it converges to this number rho naught, which is less than 1. And you get this phase diagram with 3 phases, A, C, and B. And he also, and this tricritical point is at 1 by zeta naught, 1 by zeta naught, zeta. Yeah? So he manages to compute all of this, and he manages to get the densities out in each of these regions. I write the densities of the pluses, but you can calculate all the densities using some symmetry algorithms and some intuition. So these are simulations done by Dipankar in all these regions. So focus on the zeros. Well, the labels are a bit off. You can think of the greens as the pluses and the blues as the minuses. Focus on the reds, if you will. So what seems to happen is that all the zeros seem to be clumped together. Okay. So in in A, for example, on the left, there's hardly any zero, and similarly over here on the right, there's hardly any zero. And this is this was explained. This can be explained physically through a construction which I worked on with Joel Leibowitz and Gene Spear for the totally asymmetric case when Q, gamma, and delta are 0. So what happens is that your second class particles, which are the zeros in this case, are all stuck together and they sort of move in tandem. They, up to very small fluctuations, this width is fixed and they sort of dance together. They perform both fronts perform a random walk, a simple symmetric. So that gives an explanation of all these densities. Okay, so now I come to what we worked on with Dipankar. So this model that we're working on was introduced by these people recently from a mathematical physics kind of perspective. They didn't look at the phase diagram or anything. They found some connection to some Hecke algebra, some other story. So what we have now is R different species of charges, which I'll call J's and J bars. So J runs from 1 through R. And J bar you think of as minus J. Okay? So again, so instead of having 1 plus and 1 minus, we have R different types of pluses and R different types of minuses. They are hierarchically ordered in the sense that plus R is bigger and stronger than plus 1, for example. So stuff like that. In addition, we have these conserved quantities. So the total number of charges of species J is conserved to be n sub J. Okay, that's fixed. So the number of J's plus the number of J bars is nJ's. And the bulk rules are similar as before. Larger guys overtake smaller guys with rate 1 and backwards with rate q. On the left, J bars only replace J for each J with the same kind of rates alpha, beta, and alpha, gamma, and on the right with beta, delta. So exactly the analogous story, but with many more species of particles. But there are many more conservation numbers. So the basic properties, well, it's not obvious a priori, but the little thought shows you that the system is ergodic. You can get from any state to any other state. And there's some, actually even the TASEP version is ergodic, totally asymmetric version is ergodic. And there's some charge conjugation symmetry of the system under these interchanges. So here is an example of the system, the totally asymmetric version where there's 1, 0, 1, 1, and 1, 2. Here is the graph of the phase of the transitions. So I don't know how much you can see, but you know, on each arrow I've managed to insert the rate. Okay, and if the structure looks wonderfully geometric to you, that's because there's some underlying mathematics behind it, which sort of and which ensures that there's some nice symmetry. So we're looking at the thermodynamic limit, so we want to get out the phase diagram. So what we are going to do, we are going to take the system size going to infinity and all the number of conserved charges to infinity in such a way that the ratios converge to some theta j, which is some fixed constant, which is greater than 0. Okay. So now I remind you, so our phase diagram will depend on these theta j's. So there are r of them. There are actually r plus 1 of them because theta 0 is also there. But their sum is 1. So there are r independent parameters. In addition, there is the a and the b, just like we had for the semi-permeable TASEP, ASEP. So we have an r plus 2 dimensional phase diagram, which we are able to compute exactly, and it looks like so. So of course I can't show you in r plus 2 dimensions. I show you in the AB slice. Okay. So I mean 1 by B slice, because I'm just borrowing Uchiyama's work. So there are 2 r plus 1 regions, and they are naturally labeled by the species. Okay. So remember, this is in some large dimensional space, but there are so many regions. So in each region, we are able to compute the densities, which I've just written for completeness here. I don't expect you to understand everything. But for each phase, so there are phases. There's the 0 phase. There are phases 1 bar through r bar and phases 1 through r. So those are all the phases. So for any j, I look at phase j. And for every species k, I can write down all the densities. And similarly for j bar. So the thing that I would like you to appreciate is that in phase J, for each J, rho sub k bar is 0 for all k which are less than J, which are between 1 and J minus 1. So in other words, there is no particles of type k bar for these values of k throughout the system at all. Even though there was a priori no restriction, in that phase, somehow the dynamics conspires to kick all of these people out. Okay? And similarly, by this charge conjugation symmetry, the opposite happens for in phase. We can also calculate the currents using those formulas I skipped through earlier, but okay, I don't want to go over it. So now in the last minute and a half, I just want to give you a physical idea of why this happens. And this is a generalization of this fat shock picture that I told you. This is what we call a nested fat shock. So what happens is that all the zeros, all the ones, all the way through all the J minus ones, I'm talking about phase J, they sort of sit together, okay? And the whole thing sort of moves synchronously. And the guys, you will notice that, so how should you read this? So for any species, the density of that species is the difference between the top and the bottom. Okay, that's how many particles. That's how you should read this diagram. So from this we can get out all the densities and currents. But the point is that there are two sort of trademark non-equilibrium phenomena that are happening here. One is this business which we call dynamical localization. So look at, for instance, species J minus 1. It's sitting right in the, they're localized dynamically. Oops. Okay, so that's one point I wanted to stress. And the other is this dynamical expulsion, which is what I said earlier. Particles 1 bar through J minus 1 bar are not at all in the system. So they have been kicked out of the system. Okay, so these are the two novel non-equilibrium features. On the J bar boundary, something even more interesting happens, which is that these guys are all, form this nested fat shock. They all move in unison. I'm sorry, I'll take one more minute. I have painstakingly got this video out here. So I'm going to just show this video. So Dipankar has simulated this. So I'm in a system with R equals 2. Forget the parameters. So these are the 1 bar zeros and ones. And I'm showing you the nested fat shock. So there are two shock fronts, and they are all sort of moving together until they hit the boundary. So when they hit the boundary, you see some of the ones have been exchanged for 1 bars. Now, when they hit this boundary, some of the 1 bars will be exchanged for 1. So until they hit the boundary, they all perform random oscillations or random walks. But when they hit the boundary, whatever particles enter, they quickly move in and join the fat shock and sort of move. Once they're again in the interior, they sort of move. So at this point now, you have these 3 shock fronts which are moving. Okay. So that's sort of the new kind of phenomena that we see, and we are able to explain it completely. I should say that all this is completely rigorous. It can be proved starting from Uchiyama's work, which is all the, so he has essentially done all the hard work for us, and now we sort of just stand on his giant shoulders. Okay. So thank you and sorry for going.
Yeah. Open for questions. Anyone?
Sorry, yes. Time is up. Yeah. Should I play it again? Yeah. Should I go back to the slide, or you wanted to see the movie?
Let's show the movie again.
Movie again. Yeah, so sorry. So time is upwards. So zeros are sandwiched in between the ones and 1 bars in general. But what has happened here is that we have hit the boundary, and all the ones have been swapped for 1 bars.
What are these white bits?
So the whites are the 2s and 2 bars. So we have not shown the 2s and 2 bars, because that's just going to, it's already quite confusing. I won't confuse the picture more. But So they're sort of going to move together, you see. And there's going to be exchange of particles among the ones and one bars only when this whole shock front hits the boundary.
Questions, students? I have a quick question.
Yeah.
You have in the phase diagram 1 over A, 1 over B.
Yeah.
It's symmetric about the diagonal.
Yeah, that's that particle hole symmetry I mentioned. So if you interchange the J's and J bars, ones and Q's, alphas and betas, gammas and deltas, and change the direction of the motion, you get back the same system. Yeah, so it's a